This is section 5.2, and we're going to talk about sigma notation. And you probably saw this in pre-cal a little bit. It enables us to write a sum with many terms in a compact form. And they use the Greek letter sigma, kind of like our S, and it stands for sum. The index K tells us where the sum begins, and the number below the symbol at the number below the symbol, and where it ends above. So this starts at 1 and ends at n. Any letter can be used to denote the index, but the letters I, J, and K are customary. And then here is where your formula for the kth term would be. So if you had k equals 1 to 5 of x squared, you would have 1 squared plus 2 squared plus 3 squared, etc., through 5 squared, and that would be your sum. And there's just some examples here. We do have rules for finite sums. If you have this and you have an a sub k plus b sub k, you can write those as two separate summations. Same thing with subtraction. We do have this constant value rule, which if you have here, you can multiply n times c, and that will give you that. And we have some of those in our homework, so that will be helpful for you. Now, a Riemann sum is an approximation to the area between a curve and the x-axis made by adding together the areas of a set of rectangles. We talked about the idea of using rectangles and a limit as those rectangles went to infinity to get the sum. And the limit of the Riemann sum as it approaches 0 is the integral of the function. And here we go, an approximation to the area between a curve and the x-axis made by adding together the areas of a set of rectangles. So because we don't have a formula for the area of this curve, so that's what we're going to do. And this this thing is an interactive demo. I'm not sure it'll work as I'm doing this video, but let's see if this works. And there we go. Let's see. I'm gonna have to make it smaller to get it into the video. Nope, that didn't work. I'm gonna put you on pause and get it in there. Okay, took a little bit of manipulation, but we got it in. So this is just an interactive way to look at the Riemann sum, and you have this graph. I thought this one was kind of interesting. So here, the red curve, and you've got some rectangles here, here, because it's about the curve and the x-axis, so it's where we meet the x-axis. You can change where you go. This one's set to go from -1 to 1.9. You can change those numbers. You can change the number of rectangles. Say I wanted to just do 10, and if I replot, now I've got 10 rectangles split over that amount. This is doing midpoint, and in the last section, remember, we did left and right, max, min, and midpoint. If we do left, let's see what that looks like. Okay, and then let's go back to, let's do 50 rectangles and plot. And so you can do that, and you can change the function if you wanted to, but it tells you the estimated area and the actual area that they have done with integration. So this is just kind of cool, and if you wanted to play with it, you could. So that was what I wanted to see there. All right, so let's go look at our problem set. A lot of this is just straight calculation. It's not too bad. Write the sum without sigma notation. So you've got this, and it's saying, what does that actually mean? Well, this means from 1 to 2, write this. So we have 144 times 1 over 1 plus 7. That's that piece. Plus 144 times 2 over 2 plus 7. If you simplified it, you would get that. And then it asks you for the value of the sum. And so you could do that on your calculator and get 50. Number 2, same idea, sine of k pi. So they say go from 3 to 7. So you've got sine of 3 pi plus 4 pi, 7 pi, 6, 5, 6, 7. And sine at 3 pi, remember pi is over there on the other side of the axis. And if 3 pi is over here on the left on the quadrant, let me get a graph here. Hold on. Trying to get a picture. Okay, so if we have this, so pi is over here, and the sine of pi there is 0. That's at regular pi. And then if you went, that's 1 pi, there's 2 pi, 3, 4. It's going to be 0 whether you're here or here, because sine is the second number in that unit circle, and we are not anywhere on the y-axis. So it's going to be 0 no matter how many times you do that. And so if you write out the sum, you're doing this, and then evaluating it, we know it's going to be 0. All right, number 3. Express this in sigma notation. Use 1 as the lower and k for the index. So we're starting at 1, and it looks like we go to 29. So you could have k equals 1 to 29, and it's just k, because we just change, the number increases by 1 and goes to 29. And so that's what they're asking you to find. Number 4. Okay, number 4, you are given 2 things. So let's see. This says if the sum of k from 1 to n of a sub k is 3, and then b sub k is 48, find the following values. So 7 times a sub k, well, we're just going to multiply 7 times the 3 that they told us that was. That's 21. B sub k over 48. Well, we're just going to have 48 over 48. That's 1. And then a sub k plus b sub k, we can just add those numbers, get 51. If we subtract them, we get negative 45. And on this one, b sub k minus 5 of those, of a sub k. So 48 minus 5 times 3 is 33. So pretty easy. We're just manipulating some operations on those. Number 5, evaluate this sum. Now, I want to introduce how to do that in the calculator. And the directions here are for anybody that has an older operating system, an 83 or an 84 that isn't as updated. You would have to go to second stat, over to math, and get sum. It would put sum on there. And then second stat ops, and go to for sequence. So you'd have sum, seq, and then you'd have an open parentheses. You put the function, comma, the variable x, comma, and then the lower, which is 1, and the upper, which is 11. And then you would do that and you would get it. Now, if you're on the newer ones, let me bring this over here. So let's get out of that. All right, so if you go to math and go down, you can see summation. You hit enter, and it is lovely because you are just plugging in the values. So we're going to put x there, pops us over there. We're going to put 1. We'll hit the right arrow here. It'll take us up there. We're going to put 11. We're going to go to the right, and we put negative 2x and move out of that. So that is our summation. It matches that exactly. We hit enter, and we have negative 132. So you can use your newer calculator and get it with math and summation, or if you have the older version, you have to do these two to get sum of a sequence. So either way, on my notes, I put the older because it is a little bit more to remember, but the summation is great on the newer one. Same thing here. When you do it in your calculator, Be sure you watch parentheses pretty carefully. All of the function has to be in a set of parentheses, and so if there's some in between, you've got to cover those up. All right, so you get 445 there. Number 7, k equals 1 to 7 of 4. Well, remember we had something in the notes that showed that, and we're just going to multiply 4 times 7, and that gets 28. So when we just have a number here and not a variable, you're able to just multiply these two. So 7 times 400 is 2800, and now we're starting at 3 here, so that's a little bit different. So we are having to rearrange this so that to meet our rule that k is 1. So if we let j equal k minus 2, that would lead us to k equals j plus 2. So if k is 3, j is 1. If k is 264, which is what we have up here, that leads us to j is 262. We're just writing an equivalent. So this can be 1, 262, 10 here, and then we can use our rule. So we had to kind of manipulate it to where we were starting with a different number here, and how did that affect this? So you get 2620. Let's go down. Oh, that is our last one. So let me get rid of that. So that is our last one in that section. Not too bad. All right, that should get you through 5.2.